and then I can just answer your question now, if I can anyway, and give us a little more time for that sort of thing. So you want to ask?
Yeah, let me find the question real quick.
Do you know what section it is?
Should be in homework 3 or assignment 3 under the 1.5.2 exercises.
Okay.
I'll need to find it, but I think it is question number 3.
I'm starting up my other computer so I can bring that up and see it myself.
Yeah, I just found it. It is question number 3. I just was looking at like the second sentence in there, and I just don't know how to like interpret that basically.
Oh, is that 1.4 maybe?
What do you say?
Section 1.43C.
Oh, I was looking at 1.5.2 exercises.
Oh, okay. I thought you said 1.3. Somebody else asked me about 1.4 number 3. It had a typo in it. Okay, 1.5, problem 3 about linear transformations.
Yep, that's the one.
Okay, is it the whole question or a particular part?
Well, I'm just looking at the second sentence where it's like T of E1 equals 1, 2, 1.
Yeah.
I just don't know how to like interpret that or like write it down on paper so that I can understand it.
Okay. Yeah, actually, it turns out that's absolutely critical for being able to solve the problem too. So I'm glad you asked. I'm going to switch to my document camera. Okay, so actually, I don't have a good way to get that up on the screen. Let me try this. Whew, that might actually work. So it says T of E1 is 121, T of E2 is 220, etc. Now, this is a linear transformation from R3 to R3. And from reading the section or listening to the lecture, you know that a linear transformation of some vector V can always be represented by a matrix multiplication times that same vector, left matrix multiplication. Now, E1 means the first standard basis vector. And E2 means the second standard basis vector, and E3 is the third one. So these are the same vectors that a lot of times are called I, J, and K. So when we know this, if we know that T of E1 is equal to, let me look it up again, 121, that tells me that if I were to write this as a matrix multiplication, I'm going to have some matrix here, and I don't know what it is, right? That's the first problem to be solved. But I do know this. If I multiply on the right by the first basis vector, I'm supposed to end up with this one, 121. Now, if you just think about how this is going to play out, Of course, I'm going to have 3 times 3, 9 entries in this matrix, but it turns out that it's just this one, these in the first column that are going to be used in order to do this multiplication. Because I'm going to take 1 times this number plus 0 times that number plus 0 times that number to get the 1. Well, you can see probably pretty quickly that the only way that could happen is if I had a 1 here. Now, this number and this number don't make any difference right now, because you have 1 times 1 is 1, plus 0 is 1. In the same way, this one, this entry right here is going to have to be a 2, and this entry right here is going to have to be a 1. And it's just because I'm multiplying by the first basis vector. Okay, so this information right here tells me the first column of this coefficient matrix. Does that much make sense?
Yeah, that makes a lot of sense.
Okay, now I'm not going to go through all the details, but now I have a little bit more to work with. I've got 6 more entries to go, right? But I know that if I take T of E2, I have to land on 220. Can you guess what the middle column of this coefficient matrix has to be?
Yeah, it'd have to be 220, right?
Correct. And in the same way, you can look at what it does to E3 to figure out what his third column is. Now, once you know that, then you can compute T of V for any V, because you'll just take V and left multiply it by this matrix A, or you know, I called it A here, but I think in the notes I actually was using a notation. Brackets around the T to indicate the matrix corresponding to the linear transformation T. So knowing what it does to T of to E1, E2, and E3 tells us what the matrix is.
Okay, yeah, that helps me out a lot. Thank you.
Okay, good.
I just have a follow-up on that question. I was trying some of the exercises that I noticed there. So essentially, to change the basis, we multiply by the inverse of the P matrix.
Yes.
So if that's the case, wouldn't that be the inverse of the matrix we're actually looking for?
Yeah, this that's I'm pausing because there's kind of layers to the answer to your question.
Okay.
The first layer is that this question, probably people who are in the class by Zoom can't hear the question. So let me try to repeat it so everybody knows what we're talking about. The question, and I may garble the question in the process. If I do, correct me so we get clear what we're trying to answer. This looks a lot like the change of basis stuff that we were doing in one of the sections. I don't remember if it was this one or later or earlier. So if you wanted to view this matrix multiplication as a change of basis, then could you think of this T, this T matrix that we're coming up with as the inverse of the matrix whose column vectors are basis vectors? Okay.
That was my question.
Okay, so man, that was a lot of words, but that's just a question. That's not the answer. The answer is yes, if this transformation matrix turns out to be invertible. And that's why I was just pausing for a little bit, because I want to make a distinction here. You can have a linear transformation that isn't a change of basis transformation. It's just a function that takes vectors in one finite dimensional real vector space to another vector space. Now, in this particular case, let me, I don't know.
I've tried to invert it and it does, but I was not sure if the
Yeah, this problem, change of basis was not intended.
Okay.
However, since I'm just scanning, it looks to me like the matrix you would get would be invertible. So if you wanted to interpret it that way, you could. So yes, you could.
But essentially, it could be something that just changes those vectors into something else.
Yeah, just a function from R3 to R3. And by the way, there's no reason that you can't have a linear transformation that takes vectors in R3 and creates vectors in R2. That would be fine. And if you just think about it, it all has to do with the size of the with the coefficient matrix. So if I start with this matrix here, now this has absolutely nothing to do with this previous problem. This is a new one. In order to do multiplications, I would have to have 3 entries here because I got to have a coefficient for each column, right? So you'll notice these vectors that I start with are going to start in R3, but then once I add up multiples of these columns, I'm going to get a result that's in R2. So it doesn't even have to be the same vector space. You could start in R3 and jump into R2, or vice versa. You could start in R2 and jump up to R3, or anything you like. And so, for instance, there's a really fascinating one. Virtually every property you can think of that you would ever want a transformation to have, this one has. You take the coefficient matrix of all zeros, and it produces only one thing, always the zero vector. Now, is it equal to its square? Yep. Is it easy to answer questions about? Yep. Is it useless? Pretty much, yeah. But the point is, just to be a linear transformation doesn't require that it have any nice features other than the fact that it's got to be linear. Okay. I think what I'd like to do tonight is to get started as soon as possible with this section. And the reason is, this is the last section that's on the exam. But I don't want to jump to this right now because I just want to talk about general announcements and arrangements for the exam and things like that first. So, whoops. I'm trying to switch cameras. All right. So, a couple of things. Number one, if you've been sort of watching either Blackboard or GRCC email, you probably noticed there was a flurry of activity over the weekend. And the reason is that we're coming up on the first exam, and I want all that stuff available to you absolutely as soon as possible so that whenever it is you have time to do your preparation for the exam, it'll be there. So all of these notes are posted now. All of the homework assignments are posted. And as I grade them, the solution sets for the homework sets will also be posted. So you'll notice for the one that I turned back last week, the solution sets are there as well. So, and that's intentional. It's, you know, as you're preparing for the exam, it's really nice if you can grade your own paper. And, you know, I did not read everything in detail. So it'd be nice if you could work through that. And or if you got something wrong that I did grade, well, it'd be nice to know the right answer, right? So that's why it's there. So just be aware that that stuff is out there, and we have a lot of deadlines. So we have homework due this week, today, and Thursday. And I think that's it, right? But anyway, there's a lot to do. 1 week from today is when the first exam is scheduled. Now, if you are coming to the GRCC campus to take the exam. I assume that everyone who's regularly been attending in person will be doing that. If you're not, please, well, if you're not for any reason, please let me know. But if you have been attending by Zoom, then you'll need to make arrangements with me to take the exam. So if you're planning to come to the classroom, no arrangement is necessary, other than I would, it'd be nice to have a count so I know how many papers to print off. This is a 2-hour session, and all of it will be available for taking the exam. So it's a pretty long time limit. I don't make the exams especially long. I write about the same length of exam that I would if we had an hour class. So in the past, I haven't had too many students who found the length of time available to work to be a big issue. So I don't think that'll make too much difference. On the other hand, I think there are some people enrolled in the class who are actually living a very long distance from here, like not in the lower peninsula of Michigan. So if that's the case, actually this person, I think, made other arrangements, but I was corresponding with someone in California before the semester started, and I sincerely doubt that anyone is going to fly out here in order to take the exam. So I put an announcement up on Blackboard about, you know, basic things that you need to do to make arrangements, but that should, ideally, that would be wrapped up by this Thursday. So if you are not going to be able to take the exam here on GRCC's campus, then please get in touch with me via email or phone call or something, just as quick as reasonably possible. Let me think, any other? I have not gotten any notices this semester so far about anybody who had any disability that needs to be accommodated, and sometimes that does influence exam taking. So if there is an issue, please be sure to let me know right away so that we can accommodate that. Well, I think that's all I need to say. But I do need to hear from all of you. If you are not going to be here, I need to have an email like right away. And even if you can't make the arrangements that quickly, if you could send me an email, say tonight after class, and say, hey, I need to make some arrangements. I got some stuff to work out yet, but expect to hear from me later this week. That would be a good start. So I think that has us ready to start the lecture. So let's do that. And the good news is I think this one is relatively short. And when you're probably already thinking there's too much stuff for the exam, having a short lecture is the last one is probably a good thing, right? Okay, the last thing that we want to take up for the first exam, and the last of the sort of general things we need to think about in linear algebra before we start differential equations, is inner products, norm, distance, and inner product spaces. I just ran out of room here. So what is an inner product? Well, an inner product is a generalization of the dot product that you learned in R2 and R3. So if I have a couple of two-dimensional vectors and I want to take their dot product, I just multiply the corresponding entries and add them up, and you do the same thing in R2 as you do in R3. And we learn somewhere early on in your experience with vectors that there's some things we can do with a dot product that's really quite handy. We can talk about the length of a vector. Now, you might not have seen in this formula, but you probably did this anyway. First of all, if you put double bars around it, we call that the norm of the vector. Sometimes people don't use that language until they take a course in linear algebra. Some courses just call it length, but that's what we mean, is the length. One way of expressing that is you take x dotted with x and take the square root. And if you write that out, suppose that this were in 3 dimensions. So it's x1, x2, x3. You'd have this vector would be the same as this vector, right? So it'd be x1 times x1 or x1 squared. So x1 squared plus x2 squared and x3 squared. And you can see right away that, whoops, that's great. That this would have to be positive or perhaps 0 if you had the 0 vector. So it's perfectly legal to take the square root. And this kind of formula, I'm pretty sure everybody would have seen. You may or may not have written it this way. To find the angle between 2 vectors x and y, we say that it's the length or the magnitude of x dot y is the length of x times the length of y times the cosine of theta. And then if you divide that by the length of x and the length of y, you get this handy formula, which will prove to be quite useful in higher dimensions. And the distance between 2 vectors is simply the norm of the difference in the vectors. So if you have vectors u and v, the distance between them is the norm of u minus v. And finally, the projection of u onto v. And the projection means this, I'll draw it in 2 dimensions since it's possible there. Let's say this is u onto v. So onto v, if I have a vector u, it's this idea that it's sort of like if you had polarized light and you're using a flashlight to shine this down here, this would be the length of the shadow that you would put onto v. So that distance there is the magnitude of this projection vector. So this vector right here, this little one, that is the projection of u onto v. And I have seen a variety of notations for that. That happens to be the one I write down usually. You know, sometimes people just write it out in words. That works too. So those are the 4 standard things you learn to do, say in Calc 3 or some physics course or something like that. And all that stuff is still valid. So for vectors in higher dimensions, n-dimensional Euclidean space, what we say is, well, suppose you had now n entries instead of just 3, you know, it might be 15. Well, you could still do this calculation, right? You could just multiply the corresponding entries, sum them up and say, well, that's my inner product. And that would be fine. So that is one way of computing an inner product, and it's the standard inner product on our end. It looks just like the dot product on x2 and R2 and R3. And you know, if you look at that and think, oh, I've already done that, you would be right, you have. So there are other ways to make inner products though, and I'll just mention 2. One of them, actually, I don't know why I wrote this way. It's not very helpful. It says, here are 2 other inner products. So let x and y be vectors in Rn and let A be any invertible matrix. Well, sure, but then in just a minute, I'm going to qualify it more and say it's supposed to be a positive definite matrix. So it would be ever so much better to say, let A be an n by n positive definite matrix. And if I wrote it that way, then of course everyone would immediately say, well, what's a positive definite matrix? And it's defined right here. So what is a positive definite matrix? Well, a positive definite matrix, we're assuming now that this is an n by n matrix, and this is an n-dimensional column vector. So if you take A times X, that would give you another column vector. And if you took X transpose, turn it into a row vector, then this times this would give you a single value, a scalar. Now, let me just write one out, and you'll see why we can set things like that up and expect it to work like the dot product. So I'm going to take a 3-dimensional case. I'm going to take a particularly nice 3x3 matrix. It's particularly nice for multiplication anyway. The identity, 3x3 identity. And then and I'm leaving these to be general, just so you can see what would happen if I did this. It turns out that the identity is a positive definite matrix. So what would happen if I multiplied this thing out? Well, I'm gonna do this multiplication first, the one on the right, but you could do the other one first if you wanted to, it wouldn't matter. So I'm going to take x1 is going to multiply the first column, and the result of that is I'm going to get an x1 here. Then x2 is going to multiply the second column, and I'm going to get an x2 here. And x3 is going to multiply the third column, and I'm going to get an x3 here. And then you'll notice when I take this product, it's x1 squared plus x2 squared plus x3 squared. And the reason I did this was twofold. Number one, to show you that this is nothing other than x dotted with itself, right? And so if you put the identity matrix in here as your positive definite matrix, you essentially get the dot product back in second and third dimensions. So, and it also shows that indeed the identity matrix is positive definite. If you take this form, X transpose I X, you will, in fact, in this case, you're going to get the square of the length of X, and that's certainly greater than 0 if X is not the 0 vector. So that is trying to shed some light on what this thing says here. Suppose IN is a positive definite matrix, then X transpose IX, no, it says don't suppose, IN is a positive definite matrix. Here is the proof. If I take X transpose times IX, I get a sum of squares, and as long as I didn't start with a 0 matrix, that is guaranteed to be strictly greater than 0. So the identity matrix is positive definite. The negative of the identity matrix is definitely not positive definite. As a matter of fact, it's negative definite if you wanted to define such a thing. If you take X transpose times the negative of IN times X, well, you end up with minus X1 squared minus X2 squared, et cetera, which is strictly negative if X is not 0. So this is intended to do a couple of things. First of all, to explain a little bit, what do I mean when I talk about a positive definite matrix? Well, here is one. It's the sum is guaranteed to be strictly greater than 0 unless you start with a 0 vector, in which case you will get 0. To show that there is at least one positive definite matrix, the identity, and there is one that definitely is not positive definite, the negative of the identity. Now, in general, it is not so easy to tell if a matrix is positive definite. But if it is positive definite, then you can create an inner product this way. If A is both symmetric and positive definite, then the inner product XY defined by X transpose AY is an inner product. So that's another way to make inner products. And you sort of get the flavor of it here. You'd have the transpose of the vector here, of one vector here, you'd have the other vector here, and then you have a matrix in the middle, and you multiply all that stuff together, you'll end up eventually with a scalar. And as long as the matrix is well chosen, you'll get all the properties you need for a inner product. Now, are we going to do anything with this inner product? No, other than to give it as an illustration and tell you people build inner products this way. Okay, so and one explanation of why would be this. Well, what if we thought the first entry in the if you have like an ABC for a 3-dimensional vector, if you thought that first one was 3 times as important as the last one, and the second one was 2 times as important as the last one, and the last one was as important as the last one, then if you put 3, 2, 1 down here, your dot product would weight that first pair, X1, Y1, it would weight it with a 3, it would weight the middle one with a 2, and it would weight the last one with a 1. So it would, the ones higher up in the vectors would count for more in the dot product. So it would be a way of getting something like a weighted mean, for instance. You could do that. So people do this. Another way that people build inner products is with integrals. Suppose we're looking at continuous functions on the interval 0, 1, then our vectors would be functions. So what would the inner product between f and g be defined as? Well, you take f times g and you integrate it over 0 to 1. That turns out to be a perfectly good inner product as well. That one is extraordinarily important because at least on some interval, that's what people use for Fourier series. And that's the sort of thing anyway that's going on when people digitize sound, or if they digitize video signals, for that matter as well. So these kind of things are actually quite common in practice. But we are pretty much going to be looking at the standard inner product on our end, because that's what we need for this particular course. Okay, so finally, I've been using the term inner product over and over again, but I never defined it. What is an inner product on a vector space? Well, it's a function that maps two vectors from the vector space to a scalar. And it must have the following properties to be an inner product. U inner product with itself has to be non-negative, and you land on 0 if and only if you start with a 0 vector. That's why you needed the positive definite part in the example of before. It's got to be symmetric in this sense. The inner product of U and V is the same as the inner product of V and U. So it's just like dot product. U dot V and V dot U are the same, right? So it acts that way. It has a distributive property of sorts. The inner product of U with the sum of V and W is the same as the sum of the inner product of U and V and the inner product of U and W. If you interpret that as dot product, it says this: U dotted with the sum V plus W is U dot V plus U dot W. So yeah, if you worked with dot product for a while, you're used to doing that. And this says that if you had a constant times U, take the inner product with V, that's the same as taking the inner product of U times V and then multiplying by the constant later. And by the way, since we have symmetry says you can flip the order on these, right? So if you flip the order on these, well, then the K would be in the second place and not in the first. So you can factor a constant off, whether it's on the first vector or the second vector, or for that matter, you could factor one off of each of them. Now, if the function you cook up that starts with two vectors in V and produces a scalar obeys these four rules, it is officially an inner product. And by far, the most common one is the standard inner product, which is just a generalization of dot product. Definitely most important. The one thing that you should notice here, though, is in our notation, in this case, it is really important to distinguish between vectors and scalars. Because on number 4 here, for instance, KU, take the inner product with V, it just wouldn't make any sense if that K were a vector, right? So we're bumping up against some places where it's easy to tangle up the notation. So that's just kind of the warning. Do be careful. The last thing I want to say about inner products in general is that I think I used, yes, I did, the word scalar here. I did not say a real number. So if you have a complex vector space, then if you start taking inner products there, the scalar that you produce wouldn't necessarily be a real number. It could be a complex number that's not real. That is just fine. It's still a scalar. So, and I don't know. It depends on what area you'll be working in. But in some areas, complex numbers do come up with the vector space that you're working on. Okay, so why would anybody want inner product? Well, for the very same reasons that they want dot product. Okay, so you just think of it as just a generalization of the dot product. we can compute lengths, angle between vectors, the distance between vectors, and the projection of one vector onto another. Now, I could wax eloquent on that, but I think an example would be better. So let's compute a couple. That's been written on. Okay, so page 3. Suppose u and v are this. So these are 4-dimensional vectors. Let's compute some lengths, angles, distance between vectors, and projection, just so that we all are sure about how this works. So suppose I wanted the length of the vector u. So, or you could say I want the norm of u. Well, what I'm supposed to do is take the inner product of u with itself, and then take the square root of the result. So here's u, it's 2 minus 1, 1, 3. And I think in this case, I'm just going to write dot because we all know what that means. So what do we get? 4 plus 1 plus 1 plus 9, take the square root. So that is root 15, and we'll probably want that later. The norm of v. Well, that is the norm of, and once you've seen how this is going to go, you probably don't need so many intermediate steps. Something fell somewhere. So I'm going to end up with 1 squared plus minus 1 squared plus 0 squared plus 2 squared. Take the square root. So that's root 6. And maybe no, it is the second one. Let's find the angle between u and v now. And let's call that angle theta. Well, the cosine of theta is equal to, and we have a formula for that. It's inner product with u and v divided by the norm of u and the norm of v. And that I am just taking right off of the previous page. It's just a formula. So you learn that and you're good to go. Okay, so I want to take the inner product of u and v. I'm going to write it as a dot because it's so much more convenient and it makes it look familiar. And fortunately, we already computed the length of u and v. It's root 15 and root 6. Okay, so what do we have here? 2 plus 1 is 3, plus 0, plus 6 makes 9. Now, root 15 is root 3 times root 5. And root 6 is root 2 times root 3. And so let's see, we take root 3 times root 3, we got 3. 9 divided by 3 is 3. And it looks like I got 3 over root 10. So theta is the inverse cosine of 3 over root 10. And I guess that answers the question mathematically. But personally, I find it highly unsatisfying. I still don't know. Are these like close to parallel or what? So what I'm going to do is, I don't know about you all, when I'm trying to get the picture in my mind, the radian measure usually isn't that helpful. So I'm going to do this in degrees. So mode, looks like I already set that 2 degrees. And then I'm going to take, I want the inverse cosine of root 3, or rather 3 over root 10. So second inverse cosine 3 divided by root 10. Oops. So I get about 18.4 degrees. And I don't know about you, but if I just look at this numerical description of these vectors, frankly, I have no idea what the angle between them is, but I can easily compute it with, you know, any reasonable amount of accuracy I can get just very quickly on my calculator. Okay, the distance between the vectors then. Distance between u and v. We have a formula that says it's simply the norm of u minus v. So 2, minus 1, 1, 3, 1, minus 1, 0, 2. And let's see, 2 minus 1 is 1. 1 minus itself is 0. 1 minus 0 is 1. And 3 minus 2 is 1. I forgot my norm symbol in here. Oh, no, I just totally botched it up. That's irredeemable. Okay, take the norm. And so it's just the square root of the sum of the squares of the components. So I end up with 1, 2, 3, root 3. That's the distance between u and v. And if you think about it, a distance between vectors does make some kind of sense. I don't know if this will make, if you could see this on the camera or not. Maybe if I kind of lean them up. Okay, so suppose I have one vector in 3 space and I have another vector in 3 space. It does actually make sense. How close are these vectors to each other? And you just think, we'll just pick any 2 points from here to there, and now choose the 2 points that'll give you the shortest length, and that'd be down in here somewhere, right? So it does make sense to ask the question, how close are these 2 vectors? It's just the minimum distance between 2 points, one of which is on vector u and one of which is on vector v. So that, remarkably, you can compute that almost effortlessly. And if you think about, you know, this is 4-dimensional space here, right? Does anybody have a clear idea what that looks like? Well, not me. And we could do, assuming we were doing this, you know, like with MATLAB or something, we could do it with 5,000 dimensional space. Just, you know, just type a couple commands, we got the answer. It is kind of cool that you can do this, and it has meaning. All of the stuff that you expect geometries to do will happen with these kind of calculations. So you could even, you know, define equations of planes, and, well, except usually past 3 space, we call them hyperplanes. But yeah, you could write down equations for such objects. It's just no problem. Okay, so I think that is, oh, haven't done the projection yet. So let's do this. The projection of u onto v is the inner product of u and v over the length of v, the norm of v squared, times V. And that comes from the formula. Projection of U on V is inner product UV over length V squared times V. Okay, and well, we already probably computed U dotted with V, right? Yeah, we did up here. You take the inner product of those two vectors and we got a 9. So let's not do that twice. And the length of V, I think we computed that. Its length is 6, but I've got to square its length. So maybe I will, to make the notes more clear, instead of writing 6, I'll write root 6 squared. But obviously we know this is just 6. And then you multiply by the V vector. So this is a scalar multiple of V. 1, minus 1, 0, 2. And so I have 9/6 or 2/3 times this vector right here, 1 minus 1, 0, 2. And honestly, I don't think that is such a bad form to leave it in. But, if you wanted to write it as 2/3 minus 2/3, 0, 4/3, that would be fine too. So that's the projection of U on V. Okay, any question about that? If you're comfortable with that kind of calculation in 2 and 3D, I don't think this will give you any trouble because you're just doing the same thing. It's just with more entries. Okay, now orthonormal bases. Let me kind of go off script here a little bit because I can say it so much faster. When I have to write it out, I have to be fairly careful. But when I'm saying it, I can indicate things with examples or hand waving or voice inflection that, when I'm typing, I got really nailed down. So an orthonormal basis, let's start just with an example, R3. Now R3 is composed of 3-dimensional vectors, things that look like that, A, B, C, and you could write them horizontal, vertical format, whatever, makes sense. Now, we know that the standard basis for this vector space is the IJK, but I'll write them as matrices. Now, I want to just note that this standard basis, well, it's chosen to be the standard basis for a number of reasons, one of which is just very simple to write down and it's really easy to do calculations with. But a third is that this is an example of an orthonormal basis. And what we mean by that is this. First of all, ortho refers to, it's a shortening of the word orthogonal, which means essentially the same as perpendicular. They intersect, it means vectors that intersect at 90 degree or pi over 2, 90 degrees pi over 2 radians. Now, if I take any two vectors in this basis, and this is not going to be astounding to you, but nevertheless, it is true that if I take any two of these and compute their dot product, I always get this 0, unless I take the dot product of one of these vectors with itself. And in that case, the same thing always happens. Let's pick on the last one since we haven't used it yet. If I take 0, 0, 1 and dot it with itself, I get 1. Now notice when you take a vector v and dot it with itself, what you're going to get is its length squared. But if it turns out that its length is 1, then the square of the length and the length are exactly the same thing. They're both 1, right? So every vector in this set has two features. First of all, the length of each one of these is 1. And secondly, these are mutually, maybe I'll use the old word to communicate better. They're mutually perpendicular. And of course, I don't mean that if you pick one vector twice, it's perpendicular to itself. Of course not. But if you pick two distinct vectors, any two distinct vectors out of here, and take the dot product between them, you will get a 0. And the reason for that is they are orthogonal. And remember, that is leaning on this formula right here. The cosine of theta, the angle between the vectors, is the inner product of x and y divided by their lengths. Well, if their lengths are 1, you're just dividing by 1, right? And if they are orthogonal, then that's the cosine of 90 degrees, or pi over 2 radians, and the cosine of pi over 2 radians is 0. So if they're perpendicular or if they're orthogonal, the inner product will be 0. And if they have length 1, then you take the inner product with itself, you're going to get 1. So if whenever you have a set of vectors that has this property, the length of every vector is 1, and if you pick two of them, not the same one twice, and take the inner product, you get 0, then we say that you have an example of an orthonormal set. And if it happens to be a basis, then it's an orthonormal basis. Now, there are lots of orthonormal bases even for R3. So here's another one. See if I can do it. I'm just cooking it up on the fly here, but I think this will work. First of all, if I were to compute the length of this, I take the sum of the squares of the entries. So I take 1/2 plus 1/2 plus 0, that's 1. Take the square root, that has length 1. This one, likewise, it has length 1, because when I square, I'll lose that negative. But if I take the dot product between the two of these, I get 0, right? I get 1/2 minus 1/2 plus 0 is 0. And now I just need a third one. Well, there's an obvious way to do this right there. Now I've got a basis. That's not necessarily the only way, but actually it is the only way. Since I started this way, I only have one way to finish. So here is another orthonormal basis for R3. Now that is, if you look on page 4, there's this formula right in the middle of the page, and it says this: if a set of vectors, and I use B because we were talking about bases earlier, but it doesn't matter, it doesn't have to be a basis, this is still a true statement. So we have a set of vectors, B1 through Bn. We call the set orthonormal if you take the inner product between any two that are not the same vector, you get a 0. But if you take the inner product of a vector with itself, you get 1. Well, then we say it's orthonormal. And why? Because this is essentially saying two things. The length of each vector is 1. That's this part. And this one says two distinct. Well, I don't really need to say distinct, do I? I don't need to say two. Distinct vectors in the set are, I did this in geometry. That means perpendicular. Two distinct vectors in the set are perpendicular or orthogonal. So that's all summarized in this one formula. Okay, and amazing thing, I did the standard basis here in the notes as well. Okay, now I want to show you something else with these. I still have in mind this example here. Here is an orthonormal basis for R3, just the standard basis. It qualifies. Here's kind of a strange one, but nevertheless, it turns out that this is also an orthonormal basis. Now, I'm thinking of the case of the standard basis first, because I want to show you how easy this is in the standard basis. And then I'm going to say, well, we could do it with this basis as well. So I'm going to take a vector apparently chosen at random. Of course, it's not at random. You'll notice it has no square roots or ugly fractions. But it's sort of kind of random, you know. So pick a vector that's not too awful to give an example with, 3 minus 2, 5. And I'm going to say this, because E1, E2, E3 is a basis, this has to be equal to some constant times E1 plus some constant times E2 plus some, whoops, I need to say constant 2, C2 times E2 plus C3 times E3. And of course, it doesn't take a great genius to figure this out. If you take 3 times this plus 2 times this, but whoops, minus 2 times this and 5 times this, you'll get what you want, right? So 3 times E1 minus 2 times E2 plus, what was my last one? 5 times E3 will produce this vector. Or if you prefer to think of it this way, 3 times I minus 2 times j plus 5 times k gives this vector. You could have gotten that though by dot products. And that's the, I mean, no one is informed at this point. You know, you might have learned that much in high school. But this is what's really useful. If I take this vector right here, 3 minus 2, 5, dot it with E1 and multiply by E1 plus this vector right here, 3 minus 2, 5, dot it with E2 and multiply by E2, or I, j, and then the k next. 3 minus 2, 5, and dot it with 0, 0, 1. I get this line right here. So when I take this dot product, I get 3 plus 0 plus 0. 3 times I, or E1, is the first term in that expansion. Plus minus 2 is that dot product times E2 plus, and the last one is 5 times E3. So by taking dot products, I was able to get sort of in an automatic kind of way, this expansion of 3 minus 2, 5 in terms of the basis I was working with, the standard basis. Now, why would anybody care? Well, suppose you were working with a basis where it wasn't so obvious. What coefficients should you use on, you know, let's give these names. B1, B2, and B3, because these are my basis vectors. So what coefficients should you use on B1, B2, and B3 in order to generate 3 minus 2, 5? Well, the last one you probably guessed, that's certainly going to be a 5. But you'd have to work a little harder to get this, the first two. But you can do those as dot products as well. So the basis we care about right now our basis is 1 over root 2, 1 over root 2, 0. That's B1. B2 is 1 over root 2 minus 1 over root 2, 0. And our third basis vector is 1. Absolutely key observation, this does not work otherwise, is this is an orthonormal basis. So, you know, what's the thing they used to say? Don't try this at home. Leave it to the professionals. Well, you're the professionals now. And what you know, the secret you know, is that what I'm about to do here will not work unless you're doing it with an orthonormal basis. Okay? So I would like to write whatever vector I had, I forgot already. 3 minus 2, 5. 3 minus 2, 5. I would like to write this as some constant times b1 plus some constant times b2 plus some constant times b3. And I just want to know what the constants are. B3, C3 is obvious. That should be a 5. 5 times this will give me a 5 in the last entry. But the other two, I can compute almost effortlessly. C1 is going to be this. It's going to be the vector I'm interested in. Let's give this thing a name. The vector I'm trying to build V dotted or inner product in general with the first basis vector. So that's 3 minus 2, 5. I'm going to dot that with the first basis vector, 1 over root 2, 1 over root 2, 0. And the result is 3 over root 2 minus 2 over root 2 plus 0. So 3 minus 2, 1 over root 2 is my first constant. C2, I can compute as the target vector dotted with the second basis vector. And that is 3 minus 2, 5, dotted with my second basis vector is right here. 1 over root 2 minus 1 over root 2, 0. And when I take the inner product, I get 3 over root 2, comma, plus 2 over root 2, not comma, plus. It's supposed to be a scalar, right? Plus 0. So I get 5 over root 2. And the last one, C3, is easy enough to get by inspection now. It's 5. Okay, so what that tells me is this. My vector V is supposed to be equal to this first constant, 1 over root 2 times the first basis vector. 1 over root 2, 1 over root 2, 0. Plus the second constant, 5 over root 2. 1 over root 2 minus 1 over root 2, 0. Plus the third constant, which I just declared because it came to me in a vision at night, is 5. And if you add these up, you're supposed to get the vector that we started to. Well, let's give this a try. It gives 1/2 plus 5 halves. 6 halves is 3 for the first entry. 1/2 minus 5 halves makes minus 4 halves, -2 for the second entry, and then 0, 0, and 5 for the third entry. Sure enough, that's what we wanted, 3 minus 2, 5. So the theorem, the big idea is this: if a basis for the space B1, B2, etc., through Bn is given, and you know it's orthonormal, then for any vector v in the space, you can write this as C1, B1 plus C2, B2, etc., Cn, Bn, and we simply have a formula where Ci is equal to the vector v, take the inner product with the ith basis vector, and you are done. So all that hard work we did with changing basis, there are in some cases where there's an alternative to that. You can just do a bunch of essentially dot products and you're done. And that is this right here. I'm on page 5 of the notes. So it's the thing marked equation 1. Or you can look at equation 2, says the same thing. 2 minus 3, 4 is the example in the notes. So you'll get another one for free if you read the notes. And here in the notes, I said, by the way, we know another way of doing it. That's with that multiplying by the inverse of the matrix whose columns are the basis vectors. So you have another way of doing that. And in the notes, I think I worked, well, at least I told you, there's the formula. I guess I didn't work it out, but it does work. I checked it myself. Oh, I did do it right here. So, all right. Okay, and just as a side note, really, what if you had basis vectors that were orthogonal? So they intersect each other at right angles, but they don't have length 1. They have, you know, sort of random lengths or something. What do you do then? Well, the answer is it's pretty easy to fix. What you would do is replace these V's, which were not of length 1, you just divide them all by their length, and that would normalize them. See, if you had a vector that has length 3, and you multiply it by 1/3, it now has length 1, right? So the trick is to multiply by 1 over the length, and that will turn it into an orthonormal basis, and you don't really have to do that step. You can just sort of figure out what the formula looks like if you do. By the way, I have to economize on time, but this is the point where someone should mention the Graham-Schmidt method, which answers this question. Okay, suppose we really love the things we can do with an orthonormal basis, but the basis we have to work with is maybe not ortho and not normal, neither one. It's just, you know, it works, it's a basis, but it isn't very nice for these kind of dot product calculations. The Graham-Schmidt method is a means for it's not a theoretical means. I mean, it is part of theory, but it's a practical means of how do you start with a sort of a random basis and produce from it an orthonormal basis. So there is a standard way of doing that. And as a matter of fact, I would guess, I haven't looked recently, but I would guess that, say, MATLAB, I wouldn't be surprised that it just has a built-in routine. Here's a basis. Give me an orthonormal basis that'll work just as well. Bang, you type a couple of commands and out it comes. Even if it doesn't, you could write the code and give it one. So MATLAB has the ability to write that a user can write their own functions. And this is not terribly deep. Okay, well, that's it. That gets us all the way to exercises, and that's probably not what I need to talk about right now. So, we are like way ahead of schedule, which is fine for a couple of reasons. Number one, there are even now homework sets awaiting your attention. Also, I want to show you one other document that I put up since the last time we met. So, if I can figure out how to do this, it can't be that hard. And I don't think you can see my password. Let's just see. But from this, you can guess. I think I must have been a system administrator sometime. It's monstrously long passwords. Yep, you're right. Okay, so if you go to assignments, the assignment folder, and look in here, week 5, this has a bunch of stuff, including I just went through my notes and tried to write down the major things that we've done in every section. So the reason I'm drawing your attention to this is, first of all, I hope it will be helpful to you in preparing for the exam. But in particular, this Thursday, I just told you, I just got all the material done for the, that's going to be covered on the exam. So next class session is dedicated to review. And what I would suggest, a really good place to start would be just look through this document. And every time you come across one of those topics that you think, whoa, I think I might be a little shaky on that, you try to go from the first fearful response to a focused question that you could ask. And we got 2 hours. So I will be happy to try to answer questions. I think what I would like to do is this. Let's, for the first time all semester, sorry. How about if we take a break? It is, well, let's go by my computer clock here says it's 7:09. So let's take about how long do you need for a break? 5 minutes? 10 minutes? Let's take a 7-minute break. So that'll be around 7:16 or 7:17. And besides breaking, you could also quickly look on Blackboard if you have a device to look, and just scan through there, or any of the homework stuff. Just if there's questions, I'd like to make use of the time for that. If you absolutely have no questions, I don't think I'm probably that entertaining. You know, go home and study or sleep or whatever you need. That's fine too. But I do want to make the time available for questions if you have it. So, okay, until 7:17. Unless you've had enough of me, then just go home. Oh, thank you. Oh, and don't forget to submit your homework. If you haven't already done that, send me an email and it'll be fine. It's just that when we actually need to diagonalize matrices, it's going to be a little while, a little further in the course. So what I found is, just from experience, it doesn't make a lot of sense for me to give you a whole bunch of teaching on how to diagonalize the matrix, walk away from it for at least a month. And then by the time we're ready for it, everyone's forgotten. So I tell you how to do it later. But what it means to diagonalize a matrix is, well, first of all, 2 things. what do we mean when we say a diagonal matrix? Well, here is a diagonal matrix. It simply means a matrix that has, oh, I don't have the right. Camera turn on. So here's a diagonal matrix. It has non-zero entries are restricted to being on the main diagonal, and you have zeros everywhere else. And yes, it is certainly a true statement that the identity is a diagonal matrix. Now, it might seem a little bit strange, but it's also true to say that for any n by n zero matrix, it also is a diagonal matrix, because the requirement is that any non-zero entry must be on the main diagonal. Well, all none of its non-zero entries are indeed on the diagonal, right? So, or you could state it in negatively. Off the diagonal, I have only zeros. That's true. So this is diagonal, this is diagonal, this is diagonal. Now, to say that one matrix diagonalizes another, so if we say that P diagonalizes A, then it would mean that P inverse AP is D, a diagonal matrix. And so how do you prove that? You either get out your calculator or MATLAB, you type them in, multiply this out, and see if you get a diagonal matrix. If you don't, I botched up the question. Okay?
Okay, but sorry.
So you got a particular one in mind here?
No, it was just the question on the homework, and I was just wondering if there was what I was meant to do. You know, if I have that P and I multiply by P inverse, I'll just obtain the diagonal matrix.
You should, yes.
Right? And
Let me see if I had a.
But I was sorry. At that point, I was wondering that that's like the cheap way of getting to the answer. But I was wondering if there's a
It wasn't anything more complex.
Okay, because
I know it sounds too easy, right?
I know there's probably ways of figuring out any matrix that will give you
There is.
diagonalize another matrix, but at this point I didn't know, and I was just wondering if I missed something or if it was something that we will learn later on.
So what did I give you for the P matrix? You want to read me the rows?
1, 3, 0, 0, 2, 2, and 1, 1, 1.
That look right?
Yes.
Okay, and the matrix it's supposed to diagonalize?
Oh no, there isn't one.
Oh.
So the question was construct a matrix A that is not a diagonal matrix,
Oh.
but is guaranteed to be diagonalizable by P.
Yes, and what you would do is something like this. Here, I've got a perfectly good P here, and we hope that, so this was, actually, let me just finish that line. You just picked a invertible matrix P, or did I give you that, or what?
Yeah, and I mean, I don't know if it was invertible. It turns out it is.
It
But
is.
At first, I didn't know it, so I just tried it, and then
Okay,
it was.
and that's perfectly
But
fine.
There was P, the one that I just gave you.
Okay, so what I'm going to do now is I'm going to make a diagonal matrix. And of course, that's not terribly hard. I just make up a matrix. It could be anything. It does not matter if you did this one or something totally different. It's just irrelevant. So here's one. That's a diagonal matrix. Now, if I start with this, I don't know if I've got anybody still online or not, but if I do, well, I'm making a recording, so it should be reasonable. I need to change. Okay, so if P diagonalizes A, that means that P inverse AP is diagonal. So now let's take this equation right here and multiply it on the left by P. I leave a little space. And then I get this, P times D, right? In the same way, I'm going to take this expression right here, I'm going to multiply it on the right by P inverse. Now, P inverse times P, that's the identity matrix. And P times P inverse, that's the identity matrix. And now, if I multiply on the left and right by identity, I don't do anything. I have solved for A. Okay, now, I want an A that's guaranteed to be diagonalizable. Easy. I start with a P, multiply it by D, and multiply it by P inverse. The only requirements are this. I have to choose D to be diagonal, and I have to choose P to have an inverse.
Okay.
And those are just absolutely free choices. I don't know if I even gave you the size, right?
Yeah, it's a 3 by 3, so given
Oh, 3 by
P,
3, okay.
Yeah, so given P, I can just decide what each is and then.
Absolutely.
Okay.
So let's pop back here now to the to MATLAB, or Octave, this is. So our calculation said this, A should be set equal to P, oops, times D times the inverse of P. There's a matrix that's guaranteed to be diagonalizable. And I can check this one because I've got the P available. So it should be that the inverse of P times A times P should be a diagonal matrix. And these entries here are virtually zero. You see, they get in a bunch of digits, but it's times 10 to the minus 16.
Yeah.
There's
I've already got some of that. I think it's in the homework at some point. There was something that was like 0.0001.
Mhm.
Okay, it all makes sense. I was just a little confused, but I think.
If you think about it, what I'm doing when I write an exercise, I'm trying to get you to work with the ideas, actually get your hands on them and do some calculations so that it sinks in.
Yeah.
Because for most of us, you just read it as theory.
Right.
You sort of kind of understand, but it's when you start seeing it, then you say, I see.
Yeah. No, it's always when I always read through the notes, but then it's when I try the exercise that I actually know if I understood it or not.
Yeah. So in this case, if you did not say this, but you could have said, this seems like kind of a silly exercise. Well, in a way it is, yes. But it was just to get you to play with the ideas.
Of course. No, that helps. So now I know that.
And the only reason I can think of that you would ever want to do that is if you're teaching a linear algebra course and you would like to invent a matrix that can be easily diagonalized. Okay.
That must be useful.
Now you know one of my dark secrets.
Okay. Yeah, that was it. Thank you very much.
You're welcome. Okay. Well, let's see if I've got anybody hanging around.
I have a question about the problem that you just did.
Okay.
What did you, so P was given. So we know P and P inverse, correct?
Yeah.
What did you end up choosing for the matrix D? Did you just choose random numbers?
Yes. Essentially, that is exactly what I did. Let me switch back to the camera here. I chose 3, 5, 6, or 3, 5 minus 6, maybe it is. I just wanted a matrix that had non-zeros on the main diagonal and zeros everywhere else. But if you ask me, well, why'd you choose a 3? Why not a square root of 2? Well, I didn't have a reason. It could have been anything.
Okay, so does D have to be a diagonalized matrix?
For this trick, the question was create a matrix that can be diagonalized. So the way you do it is you build it out of a diagonal matrix by multiplying by first by P, then by D, then by P inverse.
Okay. Okay.
So it's kind of the secret sauce. By the way, I think the question said to make a 3 by 3, and the reason it says that is if I didn't specify the size, surely someone would have realized, you know, if you start with a 1 by 1 matrix, it's already diagonalized, right? So any 1 by 1 matrix can be diagonalized, and I didn't want to get that answer.
And I don't think the dimensions would work anyway. If it
No,
wasn't a 3
I
by
think
3.
this one is set a 3 by 3, but that's the reason I specified a size.
Okay.
Any other questions?
I guess I was the one who asked the question about number 3 earlier. I guess, is there any way we can kind of go through that?
Yeah. Let me, I'm trying to pull it up on my other screen here. Okay, so section 1.5, number 3.
Yep.
Okay, so is there a particular part of it that you wanted me to talk about, or the
Not
whole-
really, because I didn't even know how to start it
Okay.
when I was taking a look at it. I just kind of got stumped and was like, okay, I'll just look at this tomorrow.
All right. So how about if I do this then? I will, on the spot here, invent another problem which is very like it, and then I can freely work this problem that I'm making up right now, without giving away the answers to the homework problem. But I will intentionally be giving away the process for getting that. Now, in the original problem 3, it says T of E1 is 1 to 1, T of E2 is 2 to 0, and T of E3 is 1 minus 1 minus 1. So I'm just going to do something else. How about this? 0 to 1 and 1 to 1. And I think those are linearly independent on the original one. So I just want to make sure that I don't destroy the independence property. So I think that'll work. So let's suppose we have this, and I squeezed it a little bit here. But what I know is I have a linear transformation, and it's going to start with 3-dimensional vectors, and it's going to produce 3-dimensional vectors. Also, I know this: if you take T of the first standard basis vector, that means 1, 0, 0. Take T of 1, 0, 0, you get this. T of 0, 1, 0, you get this. And T of 0, 0, 1, you get this. And the first question is this: to find the matrix of the linear transformation. And we actually have a notation for that. It's T with square brackets above it. Okay, so how do you do that? Well, the short answer is this. It is nothing other than these vectors: 0 to 1, 1 to 1, and 1, 1, 1. And why does that work? Well, fortunately, I'm writing in pencil, so I can come back and edit this. But just imagine if you take this matrix times 1, 0, 0, it's going to take 1 times the first column, 0 times the second column, 0 times the third column, and it's going to produce 0 to 1, which is what I was told to produce out of E1. And likewise, if I put 0, 1, 0, that's E2. It's going to zero out the first column of the coefficient, zero out the third column of the coefficient, and just multiply the middle column by 1. I'll get 1, 2, 1. And similarly for 0, 0, 1, I'll get 1, 1, 1, because that's what I put in the third column. Is that so far making sense?
Yep, that makes sense.
Okay, now let's go to, so that was part A, find the matrix of the linear transformation. Part B says this, compute T of 2, 3, 4 and T of minus 6, 0, 3. So what I would do is I would say T of 2, 3, 4 is the coefficient matrix, which I now know is 0, 2, 1, 1, 2, 1, and 1, 1, 1, and multiply it on the right by 2, 3, 4, the column matrix 2, 3, 4. And that looks like a mess. What do you get? 0, 3, and 4, 7 for the first entry. 4 and 6, 10, and 4 more are 14 for this one. And then 2 and 3, 5 plus 4 are 9. 7, 14, 9 is, the language is this. It's the image of 2, 3, 4 under T, is this right here. Does that make sense?
Yep.
And so for this one, this is the next part, next piece of part B. I would do just exactly the same thing. I would take this same old matrix that I have here, and then I would left multiply minus 603 by this coefficient matrix, and I'll get something. So that answers that question. Okay, good on that one?
Yep.
Now I'm trying to be practically helpful, but I don't want to just dispense numbers here. Does it make sense now if you had a similar problem, you'd know what to do?
Yeah.
Okay. So for part C, it says this, V is the vector minus 4, minus 6, 1 relative to basis B, and I hope I'm going to find out what B is here in a moment, where B is the basis specified in problem number 1. Compute W, the vector W, which is T of V. Express W in both the standard basis and the B basis. That is the coordinates relative to the standard basis and also relative to the basis B. So I got to know what the basis B is, and that says to refer to problem number 1, which, and you can't see, but I'm scrolling up here to problem 1. It says basis B is this, minus 1, minus 1, 1. 1, minus 1, 2, and 1, 1, 1. And I just wonder if that had any overlap with the other vectors in this problem. Maybe not. That would It would be good if it doesn't. Okay. Okay, so, oh, okay. I can almost guess where this is going. All right. Some of this is just supposed to be practice in change of basis. So what I have is this. I have a vector in mind, and I want to compute T of V. Now, I know how to compute T of V if my vectors I'm operating on have coordinates specified in the standard basis. You know, when this means 2, 3, 4, it means 2 times I plus 3 times j plus 4 times k, the usual thing. But this one is our coordinates relative to the B basis. So V relative to basis B is -4, -6, 1. But you could think about what that means. It means you take -4 times the first basis vector, and for basis B, the first basis vector is this. -1, -1, 1, -6 times the second basis vector. The second basis vector is 1, -1, 2. And 1 times the third basis vector, which is 1, 1, 1. And if you add these all up, well, what do we get? We get 4 -6, that's -2 plus 1 -1. And I'm switching to horizontal format only because I'm on a paper here. 4 plus 12, 16 plus 1, 17. And -4, -12, -16 plus 1, -50. Now these are vectors in the standard basis. So it's vector -4, -6, 1 in the B basis. It's vector -1, 17, -15 in the standard basis. So far, so good?
Yeah, so basically what you're saying, to go from the coordinates of V in basis B to coordinates of V in the standard basis, it's just multiplying by B.
Correct. Correct.
Okay.
Exactly correct. And if you remember, I drew this diagram in the notes once or twice. Once I have standard basis, and then a basis B, and then another basis C, and I had arrows here. One of them goes this way, and it says you multiply by matrix B. And that's what we just did here. I started with a vector V. I had its coordinates in B, and I said, well, I would like them to be in the coordinates for the standard basis, because that's how my matrix multiplication is set up. So what do? I take this and multiply it on the left by this matrix. And that is actually essentially what we did right here. This is the B matrix, these columns, and you multiply it by -4, -6, 1 on the right. Okay?
Yep, that makes sense.
All right, so what we've done so far is we're given this. And so let me just copy this to make this concrete here. -4, -6, 1. And if by some miracle I didn't make an arithmetic mistake, then we now know what the coordinates are here: -1, 17, -50. Okay, so that's how much we've got done so far. Now we are supposed to compute, the directions are to compute T of V. Okay, so I'm going to say W now is equal to T of V. And T we can get by left multiplying by this matrix right here. 0 to 1, 1 to 1, 1, 1, 1. And then I multiply on the right by V, but it's V in the standard basis. So that's minus 117 minus 15, at least we hope. The method I showed you is definitely correct. I didn't pause and check my arithmetic, so that makes me a little bit nervous. Okay, so now to find W with respect to the standard basis, I take this product here, and oh my word, I get 0. Oh, that's maybe not so bad. 17 minus 15 is 2. What's next? Minus 2 plus 34, 32, minus 15 is 17, I think. And this just says add those up. So it's 2 minus 1 is 1. So working in the standard basis, what I've determined is this: the image of minus 117 minus 15 is 2, 17, 1. And when I do this, like typing up notes or something, I always run them through a calculator or MATLAB or something to make sure I didn't botch it up somewhere. So far, so good?
So I'm just confused how they're. What is the negative 117, negative 15 again?
That is the coordinates. We were told to transform this vector here, minus 4, minus 6, 1.
Okay.
Those are its coordinates in basis B.
Okay. Yep.
So the first thing I do is I translate to standard basis.
Okay.
So minus 117 minus 15, that's standard basis. And this matrix was set up so that it worked for working in the standard basis. So that tells me that if I want to compute T of minus 4, minus 6, 1 relative to basis B, it is exactly the same as computing T of minus 117, 15 in the standard basis. This calculation I did by the matrix multiplication I had figured out in part A. So this gives me the answer relative to standard basis. So now I know this: T of V is equal to 2, 17, 1 relative to the standard basis. And you can guess now, probably the next part is that I'm going to read. I haven't read it yet. I don't know. It's probably going to say, okay, give me this in basis B. And to go down here, then I'm going to multiply by the inverse of the B matrix.
Okay. So a good way to look at it is that we found the vector in the standard basis, and the 217 comma 1 is that vector after a transformation.
Correct.
Okay.
It's not just a good way of looking at it. It is exactly the truth. That is exactly what we did. So now, if I want to get this in basis B, this is a good question even if the problem doesn't say it. How could I get this in basis B? Well, the answer is I would do this by multiplying by the inverse of the B matrix. And the B matrix is, the B matrix just has it's the ordered basis for B. You write them as columns in a matrix. So -1, -1, 1. Now I'm not actually going to compute this because it just takes a little while. You know, you got to put it in your calculator or something. But you take the inverse of that matrix and multiply it by 2, 17, 1. That's in the standard basis, and you're going to get something. And the something you get, you know, right now, I don't know what those numbers are because I don't know what this inverse is. But I do know this. This is going to be T of V relative to the B basis. So it's going to be, you know, that's going to be equal to something. That the something is this right here. Oops, can't see what I'm pointing to. It's this right here. Does that make sense?
Yeah, that makes sense.
Okay. So now let me just then part D says this. Find T relative to B. And maybe this is a really hard problem if you don't know the trick. But what you're supposed to think of is this. You'd say, well, okay, I was trying to compute this, but originally I was given this V with basis B. So I had to transform that, and I did that by multiplying by the B matrix. On the left, that was this calculation right here. And we spelled it out in detail somewhere. Oh, right here. We took these B basis vectors and we multiplied this -4, -6, 1 on the left by the B matrix to get this. So you take that B coordinates, multiply on the left by the B matrix. Then we multiplied on the left by the T matrix, because that's what did our transformation. And then this matrix right here, this is the, that's not T inverse, that's B inverse. Then we want to go back to B, and you do it by multiplying on the left by B inverse. So if you're clever, you could say, hey, look, I could just put parentheses around here. This is a recipe. If I know the matrix of T relative to the standard basis, and I have the basis, the new basis, I can compute its inverse matrix, then multiply on the right by the T matrix. This is relative to the standard basis. Then multiply by B, and that whole thing right there, that is how you compute the transformation T, but now with respect to the B basis. So if I had that all multiplied out, if I just multiplied, this would be a single matrix once I perform the arithmetic. So if I take that matrix on the left times this original V I was given, -4, -6, 1, poof, I would just come out with the answer. It's not T. It's T of V, which is the W, the matrix I call W. So in other words, our whole process for the first part was this. We started with a vector with specified by coordinates in B. First, we multiplied by the B matrix. Then we multiplied by the T matrix. Then to get back to the B basis, we multiplied by the B inverse matrix. And so you could say, well, what if you just wrap that all up in one? This thing right here would be the way you express the transformation T in the B, in the B basis. Am I connecting with you, or does that is that not working?
Yeah, well, everything you've said makes sense. I'm just trying to figure out how that like relates to what question D is asking.
He says, find the matrix of T relative to basis B. And the answer is this right here. B inverse TB.
Okay.
That
I see.
matrix product is the matrix of the transformation T relative to B. So the original matrix T, I got by being handed what T does to the standard basis vectors. So another way of looking at this product, now we don't have the numbers in front of us, but what it says is this: what if you were handed the vectors out of the B basis, -1, -1, 1, et cetera? Well, those columns are going to be what it does to those vectors. So if I, the long and the short of it is this: on this problem, I started by giving you a vector relative with coordinates relative to basis B. And then we transformed up to standard basis. Then we did a matrix multiplication to get T of V. And then we multiplied on the left by the B inverse matrix to get back to the B basis. And so what I'm saying is, if we take the T matrix, multiply on the left by V in the standard coordinates, we will get T of V in standard coordinates. And also, if we just wanted to work in the B basis, we can predict what matrix is going to work. This is going to be the matrix of T relative to the B basis.
Okay, that just made sense in my mind.
Okay, so that's the answer to part D.
Okay.
And then for part E, how do you do that? Well, you just take this matrix, use that as the coefficient on the left to this matrix here. And you should land right where you did before. And if you think about it, the reason it should work is because that's the steps we did before. We started with our original vector in the B coordinate system, multiplied by B, then transformed by multiplying by T, then move back to the B basis by multiplying by B inverse. Well, if we just gather those matrix multiplications up as one piece, then we could say, oh, look, we got a magical matrix that if you left multiply something in B coordinates on the left, it produces the transform vector in the B coordinate system. Well, of course it does, because that's what we did.
Okay, yeah, that makes sense.
Now, looking at that through the advantage of talking to someone who's seeing it for the first time, I realize that's probably a fairly challenging question. I
Yeah,
might not have
was-
figured it out as a student.
Yeah, it was mostly, well, yet again, I only looked really at the first two sentences in like the first question. But yeah, that did seem more of like I was trying to like decipher kind of what it was asking.
Yeah.
But yeah.
And it's easy for me because I've done it a bazillion times. It's like when you hop on your bike and start riding. Well, you don't think about it anymore, right? But there was a day when that was a challenge. Okay, any other question? All right, well, if that's it, I guess I'll be signing off for the night, and I'll see you on Thursday.